Okay, so all this stuff here is going to play back into this stuff and having another way to solve for all of these things. Okay, so what we know is like the initial angular acceleration is known because it's just based on how fast I'm throwing the ball. So we can say like, let's just say that I know the acceleration of the ball initially, which you can test with some different things, but you have a known force that is accelerating the ball at by a certain amount. Okay, so the acceleration at the second point is equal to alpha 1 times r1 over r2. Okay, so r1 is this distance, r2 is the shorter distance, right? So r1 is always greater than r2, which means that the angular acceleration at the center is faster than at the outer edge, which makes sense, right? So that's logical. So what I can do is I can solve for alpha, and then I can know that the acceleration at point 2 is equal to alpha 2 times r2, and then I can put in that acceleration at point 2. I can come in and I can plug that back in over here, and I can solve for a bunch of cool stuff, right? So what we find is that if you reduce the radius at the second point, the angular acceleration increases, but the tangential acceleration in a line is always going to be the same, right? But you're gonna do more revolutions, but the total distance traveled is going to be equal given the same amount of time.